Alright, I knew I was going to get cut off on the last one, so I decided to start one last video. We have 3 more examples I'd like to get through, and then we've covered all you need to know about sequences. So here's a sequence, 2, 4, 8, 16, 32, 64, and we need to represent it with a recursive formula, with the formula for the nth term, or the general term, and in function notation. So first we need to figure out which type. Is it arithmetic, is it geometric, or is it something else? So to get from 2 to 4, we could either multiply by 2, or we could add 2. To get from 4 to 8, we could definitely multiply by 2, but we're going to add 6, so it's definitely not arithmetic. It is in fact geometric because we're multiplying everything by 2 in order to get to the next terms. Which means that R is 2 because we're multiplying by 2 every time. A is 2 because this is term 1 over here, and it's geometric. So part A, with a recursive formula. So we have to say what we're starting with. So term 1 is 2. Term n, that's the part we need to figure out. So it's in general. Actually, I'm going to write this slightly differently. Nope, I don't want to erase that. All right, term n is equal to r times term n minus 1, and n is greater than 1 in this case. R we know is 2, so we're going to sub that in. So term 1 equals 2, term n equals 2 times term n minus 1. So term 2 would be equal to 2 times term 1, which would be 4, and greater than 1. If we didn't have this part in here, term n is equal to 2 times the previous term, we wouldn't be able to get the next term. We'd be missing information, and it's not recursive if you don't know what comes before. Let's check this. So term 2 would be equal to 2 times term 1. 2 times 2 is 4. Term 3 would be equal to 3 times term 2, which is 3 times 4. Or sorry, not 3. Term 3 is 2 times term 2. So 2 times 4, which is 8. So this is in fact correct. It works for this sequence. So this is our recursive formula. Part B. We need the formula for the general term. And we've worked with this one a little bit already. So term n is equal to a times r to the n minus 1. In this case, we don't have to state what the first term is because it's part of the equation here. So term n is equal to a, which is 2, times r, which is also 2, to the n minus 1. Now, when we have same base, we can add the exponents. There's an invisible one here. So we would get that term n is equal to 2 to the exponent 1 plus n minus 1. Well, 1 plus n minus 1 is just n. I'm going to shrink this down so I can fit the last little bit in here. So this is actually equal to term n is equal to 2 to the exponent n in simplified form. So that's the general term. And finally, we need this in function notation. We already have a very simplified equation right here. So it's pretty much the same thing here. F of n is equal to 2 times n, and n is an element of the natural numbers. That last part is important when we're talking about function notation. All right. Apparently my numbering got a little messed up. Example 5, 6, 7, 9, 10. That's okay. This should actually be example 8, I believe. Write a recursive formula for each sequence. So part A, here we would possibly add 4, but if we try to add 4 to the next part, it's obviously not arithmetic, so let's try multiplying. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54, which means that it's a geometric sequence. A is 2, R is 3, and term n is equal to R times term n minus 1, where n is greater than 1. Plug in what we know. R is 3, term n minus 1. So if we just say this part, again, we don't have enough information. We have to say that term 1 is 2, term n is 3 times term n minus 1, and n is greater than 1. All of this needs to be stated in order to be able to find the next term. Maybe I could shrink this down a little, just to make sure we have room for the next one. All right. B, 1, 2, 4, 7, 11, 16. If we try multiplying, well, 1 times 2 would be 2. Come on. 1 times 2 would be 2. 2 times 2 would be 4. But then it falls apart because 4 times 2 is not 7. Let's try adding. 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 3 is 7. Plus 4 is 11. Plus 5 is 16. It doesn't have a common ratio. It doesn't have a common difference. Therefore, it's not arithmetic or geometric, but it is still a sequence. So we're going to have to find the recursive formula and kind of make it up to make sure that it fits. It's not going to fit one of the formulas we already know. So one way that students often like to look at this is put it in a table. You've done this kind of thing with patterning before. So term 1, 2, and there goes the pen again. So we have 6 terms that we know. 1, it's not letting me write. 3, 4, 5, and 6. This mess over here should be a 2, but it doesn't want to let me write for some reason. Term 1 is 1. Term 2 is 2. Term 3 is 4. Term 4 is 7. Term 5 is 11. Term 6 is 16. Now let's look what's happening here. From here to here, we add 1. From here to here, we add 2. We add 3. We add 4. We add 5. So you'll notice that the thing that we're adding here is 1 less than the term number. So we're adding 2 to get term 3. We're adding 3 to get term 4. We're adding 4 to get term 5, and so on. So we can turn this into, oh my goodness. Okay, we can turn this into a recursive formula by saying that term 1 we know is 1. Term n is the previous term, because we always have to have the previous term somehow in a recursive formula, plus n minus 1, meaning the term number subtracting 1, and n is greater than 1. This is our recursive formula, and we're actually going to check it to make sure that it's correct. So let's pick one of the higher ones. Let's say term 6 should be term 5 plus 6, because it's a term number, minus 1. So term 5 we already know is 11. 6 minus 1 is 5. 11 plus 5 is 16, and term 6 is 16. So that means that our formula that we've come up with is correct. Now, all right, I'm going to clear everything on this page because it's getting a little chaotic for my liking, so that we can do the final example. Part C. 4, 5, 20, 100, 2,000. So this one might take a little bit of playing with and playing around with, but I'm just going to show you how this one works. So we start with term 1, which is 4, and we actually have to say term 2 is 5. Once we have those, then we can use those to generate the ones after. So if you take these two terms, multiply them together, you get that term. If you take these two terms and multiply them together, you get that term. And if you take these two and multiply them, you get that term. So it's the previous term times the term that is previous to that gives you the new term. So term 1 is 4, term 2 is 5. Term n is term n minus 1, which is the previous term, multiplied by term n minus 2, meaning the term that is 2 before that, and n is greater than 2. Let's check this one just to be sure. Let's say we have term 5 here. This is our last one. So term 5 we know is 2,000, but that would be equal to term 5 minus 1 times term 5 minus 2, which is term 4 times term 3. Term 4 is 100. Term 3 is 20. And 100 times 20 is actually 2,000, which means that this is our recursive formula. And yes, you do need to write all of that I just put in the box. All right, one final example. Represent this sequence 0, 3, 8, 15, 24, 35 with a recursive formula in function notation and with the formula for the nth term or the general term. So this one, not arithmetic because you're not adding a common difference. It's not geometric because you're not multiplying or dividing by a common ratio. So let's look at what we're doing here. We're starting with 0, and we're adding 3. Then we're adding 5. Then we're adding 7. Then 9. Then 11. So we're adding the odd numbers. So the recursive thing in words would be start with 0, and then add the odd numbers every time. In general, we can write even numbers like this. 2 times, let's call it k. K could be any number, doesn't matter. And the odd numbers we could write as 2 times k plus 1 or 2 times k minus 1. So for example, if you want an even number, let's say k is 5, 2 times 5 is 10. It's an even number. If you're looking for an odd number, 2 times 5 plus 1 would be 11, or 2 times 5 minus 1 would be 9. Both of those are odd numbers. So this is just examples of what I was talking about up here. So for this one, we're starting with this. So this is term 1. Recursive means you have to rely on the previous term and add, subtract, multiply, divide something in order to get the next term. And we've talked about how we're adding odd numbers here. So 3, 5, 7, and so on. So in this case, we are going to have term 1 is 0, and term n is equal to term n minus 1, the previous term, plus 2n minus 1, where n is greater than 1.